Here is an assumption that holds up almost everything we believe about the universe. Pick a direction, any direction. Point the most powerful telescope you have at it, and look as far as the light will let you. Now turn around and look the other way. The rule says those two views should, on the largest scales, look essentially the same. Same scatter of galaxies, same web of matter, no edges, no center, no special regions, nothing that stands out. A universe that is zoomed far enough out, smooth and even and boring in every direction. That assumption has a name, and almost every map we've ever made of the cosmos depends on it being true. In early 2025, a team of astronomers found something that may not let it stay true. A single connected structure so vast it strains the rule to its breaking point. They named it Quipu, and it should not be allowed to exist. The assumption is called the cosmological principle, and it's the quiet foundation under modern cosmology. It says that on large enough scales, the universe is homogeneous and isotropic, homogeneous meaning evenly mixed. Isotropic meaning it looks the same in every direction. Lumpy up close, sure, stars, galaxies, clusters, but smear your vision across a big enough patch and the lumps average out into uniform cosmic soup. This isn't just a nice idea. It's load-bearing. The equations we use to describe the expanding universe, to estimate its age, to weigh its dark matter and dark energy, all assume the cosmological principle holds. If it doesn't, a lot of carefully built numbers start to wobble. So the obvious question becomes, how big is big enough? At what scale does the universe finally go smooth? For decades, the rough answer was a few 100 million light-years. Below that, structure. Above that, uniformity. That was the deal. Galaxies could clump into clusters, clusters into superclusters, but somewhere past a certain size, the clumping was supposed to stop. The deal assumed nothing could get much bigger than that. Quipu did not get the memo. The structure surfaced through a project called ClassX, a survey that maps the cosmos not by ordinary starlight, but by X-rays. Galaxy clusters, the biggest gravitationally bound objects we know of, are wrapped in gas so hot it glows in X-ray light, which makes them beacons for tracing where the universe's matter piles up. A team led by Hans Bohringer at the Max Planck Institute combed through that map of the nearby cosmos, roughly 425 to 800 million light-years out, looking at how the clusters were arranged. And they noticed the clusters weren't scattered. They were strung together. One enormous central filament with smaller filaments branching off it, all part of a single connected whole. The shape reminded them of an ancient Incan device, a system of knotted cords once used to record numbers and information. They named it Quipu, and then they measured how big it actually was. Quipu stretches about 1.3 billion light-years from end to end. That number is almost useless to a human brain, so anchor it to the only galaxy you live in. The Milky Way is roughly 100,000 light-years across. Quipu is more than 13,000 Milky Ways laid end to end in a single connected chain. Now weigh it. The structure holds something like 200 quadrillion times the mass of our Sun. Written out, that's a 2 followed by 17 zeros. It's roughly 200,000 times the entire mass of the Milky Way, galaxies and dark matter and all, gathered into one superstructure. And remember the rule. The universe was supposed to go smooth a few 100 million light-years up. Quipu is several times longer than that ceiling. It is, by definition, the thing that wasn't supposed to be there. Here's why this is more than a fun record to put on a poster. First, the size itself is the problem. A structure this large isn't just impressive, it's in tension with the cosmological principle. If the universe still has lumps this enormous at 1.3 billion light-years, then big enough to be smooth keeps getting pushed further out than the theory comfortably allows. Second, Quipu isn't alone. Bohringer's team didn't find one giant, they found 5. Quipu was simply the largest of a set of superstructures hiding in the same volume of nearby space. Together, those 5 hold a startling fraction of everything around us, around 45% of the galaxy clusters, about 30% of the galaxies. Roughly a quarter of all the matter. All concentrated into structures filling just 13% of the volume. Third, and most quietly unsettling, an object this massive bends the measurements we take through it and around it. It tugs on the motion of galaxies. It distorts the light passing by. And it nudges the very numbers we use to clock how fast the universe is expanding. That last one matters more than it sounds. Because the honest reveal here isn't a twist about what Quipu is made of. We know what it's made of. The reveal is what Quipu represents. For years, cosmologists treated the cosmological principle as essentially settled, reliable, the kind of assumption you build on without checking. Quipu is part of a growing pile of evidence suggesting that confidence was premature, that the universe may be lumpier, more structured, and less uniform on the largest scales than the foundation of our models requires. The team behind the discovery is careful about this, and so should we be. Boehringer has pointed out that Quipu is the largest structure in the nearby universe, and that bigger ones very likely exist if you search larger volumes. This isn't proof the principle is broken. But it's a crack worth staring at, because if the universe isn't as smooth and even as we assumed, then one of our most basic questions is back on the table. Is the cosmos really the same in every direction at all? And that question lands directly on the biggest open wound in modern cosmology. It's called the Hubble tension, and it has been keeping physicists up at night for a decade. The problem is simple to state and maddening to solve. We have two solid ways to measure how fast the universe is expanding. One method reads the light of exploding stars relatively nearby and clocks the recent expansion. The other reads the faint afterglow of the Big Bang itself and clocks the expansion of the infant universe. Both methods are careful. Both have been refined for years. And they disagree. They give two different speeds for the expanding universe, and as each measurement gets more precise, the gap refuses to close. It only sharpens. Something in our picture of the cosmos is incomplete, a missing ingredient, a wrong assumption. And structures like Quipu, which warp expansion measurements through sheer mass, are a hint that one of those buried assumptions might be the culprit. Step back and a pattern comes into focus. Over the last few years, the surprises have stacked up. Structures too big for the rules, an expansion rate that won't reconcile. Hints in some surveys that galaxies across the sky may not be oriented as randomly as a perfectly even universe predicts. Each of these on its own is arguable. Together they rhyme. It would be easy to shout that cosmology is broken. That's not quite the truth, and the truth is more interesting. The standard model of the universe is extraordinarily successful. It explains a staggering amount, but it was built on a handful of simplifying assumptions made when our maps were cruder. And we are now mapping the cosmos precisely enough to test those assumptions for the first time. Some of them are starting to creak. That's not failure. That's the moment right before a model either gets patched or gets replaced. And one of the proposed patches is genuinely strange. So suppose the universe really isn't perfectly even in every direction. Suppose there's some overlooked feature that could distort our measurements, ease the Hubble tension, and account for a cosmos lumpier than the rules allow. What single property could do all of that at once? In 2025, one team proposed an answer almost no one expected. What if the entire universe is spinning? Not the planets, not the stars, not the galaxies, which we already know rotate. The universe itself as a whole, turning slowly around some axis. It sounds absurd on its face, because we're trained to picture the cosmos as expanding outward uniformly, with no center to orbit and no spin to speak of. The standard model assumes exactly that, no rotation in any direction at all. But in March of 2025, a team including Istvan Zapudi at the University of Hawaii's Institute for Astronomy decided to test what would happen if they relaxed that assumption. They took a mathematical model of the universe, and they added one new ingredient, a tiny amount of overall rotation. Then they checked whether the results still matched what we actually observe. It did, and it did something more. Zapudi put it by reaching for an old Greek phrase. The philosopher Heraclitus said panta rei, everything flows. The team's version was panta kyklautai, everything turns. The rotation they needed wasn't violent, it was almost unimaginably gentle, so gentle you'd never feel it. Their model suggests the universe would complete a single rotation roughly once every 500 billion years. To put that in perspective, the universe is only about 14 billion years old. It hasn't finished even a fraction of one turn since the Big Bang. This is a spin so slow it's effectively invisible to any direct measurement we currently have. And yet, in their math, that whisper of rotation was enough to do the one thing cosmologists have been struggling to do for 10 years. As the team reported in monthly notices of the Royal Astronomical Society, the rotating model resolved the Hubble tension. The two stubborn expansion rates, the nearby one and the ancient one, could be reconciled. As Saputi put it, much to their surprise, the model with rotation resolved the paradox without contradicting current astronomical measurements. And crucially, the idea breaks no known laws of physics. A slowly turning universe would also mean the cosmos has a preferred axis, a special direction, which would mean it is not perfectly the same in every direction after all, exactly the kind of large-scale asymmetry that giant structures like Quipu keep hinting at. The crack in the patch may be describing the same thing. Now the necessary caution. The spinning universe model is one paper, an early one, and its authors are the first to say so. It's a promising mathematical result, not a confirmed feature of reality, and the next step is building it into a full simulation and hunting for any real signature of cosmic spin. Quipu, equally, is a real structure but not yet proof the cosmological principle is dead. These are clues, not verdicts. What makes them worth watching is that they keep pointing the same direction. A decade ago, the smoothness of the universe and the steadiness of its expansion felt like solved problems, footnotes in a textbook. Now there's a structure 1.3 billion light-years long that won't fit the rules, and a serious proposal that the whole cosmos might be slowly turning. That's how fast the ground is shifting beneath cosmology right now. So what do you think, is the universe perfectly even? Or is something off axis? Tell me below. And if this is your kind of question, subscribe.